Hi guys, welcome to the next section, Collaborative Filtering. In this section, we will see topics such as Introduction to Collaborative Filtering, Introduction to the R package, Recommender Lab, and Extensible Recommendation System Framework in R, Collaborative Filtering Use Case and Data, Designing and implementing the steps involved in building a collaborative filtering project. Now, we move on to the first video of this section that deals with Introduction to Collaborative Filtering. In this video, we're going to take a look at memory-based approach, model-based approach, and latent-based approach. There is a database of user ratings for products where a set of users have rated a set of products. Collaborative filtering algorithms can give ratings to products yet to be rated by a particular user. It leverages the neighborhood information of the user to provide such recommendations. The input to collaborative filtering is a matrix, where the rows are users and the columns are items. Cell values are the ratings provided by the user for a product. Ratings of products are ubiquitous in today's internet world. A rating system deployed to capture user preferences. Preferences are typically captured by a rating system, where the ratings are defined as stars or a points system. Based on the underlying technology, collaborative filtering can be an online system where the whole user product preference matrix is loaded into the memory to make recommendations for a user and his yet-to-be-rated product combination. Model-based system, where an approach similar to clustering is used to group users with similar preferences, and later use those cluster centroids to make recommendations. There is a user rating matrix where several users have rated several products. The goal of collaborative filtering is to predict the ratings for all products unknown to the user and produce the ratings for the top N list of products unknown to the user. The underlying premise of the collaborative filtering algorithm is that if two users agree on ratings for a large set of items, they may tend to agree for other items too. Let us use a small R code snippet to explain this concept. Assume we have 7 products, A, B, C, D, E, F, G, and 2 users, that is, user A and user B. We also have the ratings provided by both of the users for some of the products. The ratings are a range of numbers from 1 to 5, with 1 indicating a poor rating, 5 indicating a good rating, and 0 indicating no rating. Let us run the code. Both of the users agree on ratings for products A, C, D, and E. User A has not seen and therefore not rated products B and F. We see that user B has rated those products. As both the users agree on most of the products, we can use user B ratings for product B and F and fill in these missing ratings for user A. The example is based on a user-based collaborative filtering approach. We hope the example serves to introduce the collaborative concept. There are other approaches to collaborative filtering, that is memory-based approach, latent factor-based approach, and model-based approach. The memory-based approach is further classified as user-based approach, and model-based as item-based. Having discussed the hypothesis behind the algorithm, let us look at the approaches to collaborative filtering. Let's start with memory-based approach. The memory-based approach to collaborative filtering loads the whole rating matrix into memory to provide recommendations, hence the name, memory-based model. User-based filtering is the most prominent memory-based collaborative filtering model. As the user and product base grows, scalability is a big issue with memory-based models. For more on similarity measures, you can visit this website. Similarity measure is a quantitative measure used to compare 2 vectors. They return large values for similar objects and either 0 or smaller values for dissimilar objects. Similarity measure is typically implemented as a real-valued function. Pearson Coefficient measures the correlation between 2 variables. A value of +1 indicates that 2 variables are highly correlated, and a value of -1 indicates negative correlation. The Pearson correlation score finds the ratio between the covariance and the standard deviation of both objects. The cosine similarity is the angle between 2 vectors. Let us say U base to A does not have the ratings for P5, P7, and P9. We take the average of ratings for these products from the k neighbors of U base to A and use that as the ratings for U base to A. Next, we will see the model-based approach. The model-based approach addresses the scalability problem seen in memory-based approaches. Compared to the user-based approach, where the recommendations came from leveraging a user's neighbor's preference, the model-based approach leverages product similarity to make recommendations. The premise is that users will prefer those products similar to the ones they have already rated. The first step in this approach is to calculate the product similarity matrix. Let us say there are a set of products P1, P2 till Pm. An M into M matrix is constructed to begin with. Once again, Pearson Coefficient or Cosine Similarity is used as a similarity measure. For efficiency purposes, instead of building a whole M into M matrix, a smaller M into K matrix is built, where K is less than M, K most similar items. This is a small code snippet to illustrate model-based approach. We have three users, user A, user B, user C, and three products, A, B, C. We also have the ratings the users have provided for these products. The ratings are in a scale from 1 to 5. With this line of code, we will convert the user rating into matrix form. Let's run the code snippet. As you can see, here is final rating matrix summarizing the user product ratings. Let us use this ratings matrix to build a product similarity matrix. We are using the core function from the base package to calculate the similarity matrix. Let us say we want to find the ratings for product B for user A. The most similar product to product B is A, as it has a higher score compared to C. In a real-world example, we will have multiple similar products. Now, the score for B for user A is calculated as 2 into 0.5 plus 3 into negative 0.945 divided by 0.5 plus negative 0.945. The predicted rating for product B for user A is calculated using similarity measures between B and A, and B and C weighted by the respective ratings given by user A for A and C, and scaling this weighted sum with the sum of similarity measures. The similarity matrix of products are pre-computed, and therefore it does not have the overhead of loading the whole user ratings matrix into memory. The last approach is the latent factor approach. It leverages matrix factorization techniques to arrive at recommendations. Recently, these methods have proved themselves superior to item-based and user-based recommender systems. This was one of the winning solutions in the famous Netflix recommendation competition. This website is a good place to understand the various techniques used in the Netflix challenge. Matrix factorization or matrix decomposition is the method of splitting a matrix into multiple matrices. The product of these matrices will produce the original matrix. For more on matrix decomposition, you can refer to Wikipedia page. Singular value decomposition is a matrix factorization technique used in machine learning to reduce the dimension of the input data. The idea is to find the directions of maximum variances and retain only those as they can explain considerably the variation in the data. There's a wonderful article by Maller Mayheb at medium.com, which gives the intuition behind using SVD for recommender systems. Let us say our original matrix is M into N, where we have M users and N products. Applying SVD on this matrix, we get M into F matrix for each user in M. We have F features or factors. N into F matrix for each product in N. We have F features or factors. Applying SVD matrices with missing values is not possible. Our ratings matrix will have a lot of missing values. Simon Funk proposed a new method, now called Funk SVD, to do SVD on large matrices using numerical optimization methods and gradient descent. Funk SVD is implemented in the Recommender lab package. The dimension F in M into F and N into F represents the latent factors. Hence, the name of this method is the Latent Factors method. These latent factors represents some of the hidden features. For example, in a movie database where our items correspond to movie, one or a couple of latent factors may point to the box office success of the movie. Each user has a vector now from the M into F matrix. Similarly, each product has a vector now from the N into F matrix. For a given user and item, multiplying their respective vectors gives the rating for that item specific to that user. Can you guess why? Here is where the features or factors comes to play. The features or factors are shared by both the matrices. The ratings in the original ratings matrix is now decomposed into a set of features. Thus, when we multiply the user vector 1 into F with the product vector 1 into F, we get a scalar value, which is the rating for that product by that user. Let us look at this code snippet that predicts the recommendation for unknown products for users. We use the SVD function from the base R package to decompose the ratings.mat. Ratings.mat is the same ratings matrix we use to explain item-based similarity. User A vector is the vector representing user A, and the product B vector is the vector representing the product B. Ratings user A prod B is the product of these two vectors representing the ratings of product B by user A. Let's run it. Now that we have illustrated all three different approaches to build a collaborative filtering method,